Section 6.2 is trigonometric integrals. It's split into two halves. We have A, which will be specifically trigonometric integrals, and then part B in subsequent videos will be trigonometric substitution. So the first thing we need to work on is how to integrate more complicated trig functions in integrals. Some very useful identities that we'll have along the way are listed on this first page here. The Pythagorean identities, all three of those, remember that these two can be derived from this first one on the left here by dividing by sine squared or cosine squared and solving for remaining terms. And then another very useful one is the half angle identity. And namely, these two lines of this half angle identity are what's useful. Cosine of 2x is equal to either of these bottom two half angle or expressions involving sine squared and cosine squared. We're going to use this later to reduce the powers of a sine function or a cosine function in an integrand. So in other words, we'll solve for sine squared of x so that it involves this term and another term, and we'll be able to substitute that sine squared for cosine 2x plus or minus 1 or something like that with a factor of 1/2. So that we'll see later, but it's going to be handy to have these formulas around, either memorize them or write them down somewhere and always have them available pretty much for the rest of the semester. Okay, so to get started, we'll look at integrals of the form sine to the m cosine to the n power of x. And we start out with just sine cubed of x. What you'll learn is that typically odd powers of sine and cosine lend themselves to be a little bit easier than all even powers of sine and cosine in an integrand. So we'll start in the lighter version. The first thing we want to do is rewrite sine cubed as sine squared of x times sine of x. Okay, this allows us to use the Pythagorean identity. In the next line, sine squared of x is 1 minus cosine squared of x. So we make that substitution. What we have in mind is this. If we introduce cosine squared and we have sine here, sine of x is an extra copy dx, it's suggestive that this might be some sort of du below here. Sine x dx is some sort of du. And that's exactly what we're working towards. So once we replace sine squared x with 1 minus cosine squared x, we'll have 1 times sine x, and that's this term. That's easy to integrate on its own. And then we'll have negative cosine squared x times sine x. And this is where we'll use a u substitution. U will be cosine of x, and du will be sine of x, or negative sine of x dx. We'll see that below. So that's what we were working towards, and that's your goal. You have to have a little bit of foresight in these problems, and that's what we've gotten to in the next line. We realize with this u substitution that we let u be cosine of x, this term will become u squared, and du is negative sine x dx, and that's exactly here. And we even have the minus sign, so that minus sign will change to a plus sign in the next step. Notice that this just became its own integral, sine x dx. It's by the linear property of integrals. We can split off sums, added terms, added functions underneath the integral, provided both integrals exist. And we integrate this one to get negative cosine x. And we integrate, or we have the other one set up as plus integral u squared du. Now this is just a power rule on the power function u squared, and we get 1/3 u cubed. And remember that u is cosine of x. So in the end, we substitute for u to get 1/3 cosine cubed of x in this term. Our first term is negative cosine of x. Those are all added up with a plus c. And this problem is finished. So the point is to split off even multiples or even powers of sine or cosine out of the expression, leave an odd first degree or to the power of 1 sine or cosine off to the right, and as long as they are different, we'll probably have a nice u substitution that can be used. Typically, you'll always use a Pythagorean identity in there too as well. Let's see another one. So we have sine to the 4th x cosine cubed x, and we're trying to take the integral of this. Our strategy is very similar. We've got an even power for sine of x, so we'll leave that one alone for now. We'll look at cosine cubed of x. This one we can easily take a power of a factor of cosine to the first power of x out, and we do that as cosine squared x cosine x. And then we realize that cosine of x will be the du for u equals sine of x. And the only thing we need to do is switch cosine squared of x to be in terms of sine. Well, luckily it's an even copy or even power of itself, so we can use the Pythagorean identity in this case directly since it's cosine squared x. And we get 1 minus sine squared of x. Now we need to distribute this product across this term. And we have the following: sine to the fourth x minus sine to the sixth x times cosine of x dx. This is a very nice looking du to u equals sine of x. And that's carried out down below. U is going to be sine of x. And we've split the integral up after multiplying both of these through. That's not necessary, but it's nice to do potentially. We've got for sine to the fourth x cosine x, we have this. And this one, we have this integral. So just distributing the cosine of x factor over that difference and then splitting up the integral over the difference into two separate integrals. So now we have a du for both of these, and we'll end up with two integrals, u to the fourth du corresponding to this, and u to the sixth du. And that's a nice straightforward power rule in both cases. And we have the following here. And remember to back out of the substitution, u is equal to sine of x. And at the very bottom, we've got 1/5 sine to the fifth x minus 1/7 sine to the seventh x plus c. So that takes us through that version. What's consistent here is we peel one multiple off of this odd power of cosine. If it had happened to be an odd power of sine, we'd peel an odd power off of that. If this happened to be odd, it really wouldn't have mattered. We didn't use any Pythagorean identity for this one, so these powers would have just been odd numbers had that been the case, and this problem would have gone just the same. Now, what happens when they're both even? That's a more difficult case. So let's see what we can do in that regard. So let's start simple. Let's integrate I equals cosine squared of x with respect to x. So first line, we write it down and realize, oh, we don't have any version of sine that we can lend to this for a u substitution. There's no d. We can't get sine out of cosine squared unless we use a Pythagorean identity, but then we've got 1 minus sine squared of x in our integral, and we're kind of back in the same, we jumped out of the pot and into the fire at that point. So we haven't really pushed the problem in any nice way. So what we'll use is the half angle identity, okay? And the half angle identity, recall from the first page, is cosine, just to list it here, cosine 2x is equal to cosine 2 cosine squared x minus 1. Okay, when we solve for cosine squared of x, we'll add 1 to both sides of this and divide by 2 on all sides, and we'll get exactly what we've got here in the integrand. Okay, so we've replaced cosine squared of x with this expression after solving for cosine squared x and the half angle identity. I encourage the reader to carry out the details over here just to complete this. You'll do this many times this semester from here forward. And once we've done this, we realize that we've reduced this power of cosine from 2 to 1. So that should help us out. Let's see what happens. So we have a 1/2 times both of these. We'll just factor the 1/2 out in front of the integral. And it looks like we're splitting the integral over the sum. So really we'll have 1/2 integral cosine 2x. That's this multiple in integral. And then, it's here, plus the integral of 1/2 1 dx. And that's this term. Of course, the one on the right, this last one, is very easy to take care of. So it's just that it's going to integrate to x. So we'll turn our attention to this. And we realize that there is, turn our attention to the integral of cosine 2x dx right here. Good. Now we'll realize that this is only merely a u substitution integral. So we'll let u be equal to 2x. And du is equal then to 2 dx. Take the integral, or take the derivative of 2x to get 2, and du dx is 2, so du equals 2 dx. So that means that dx is equal to 1/2 du. I'll write that line just so we see it. This tells us that to swap for dx, 1/2 du is dx, and that's exactly what goes in for this dx right here in the next line. Or that's exactly how we integrate it. Maybe the details just aren't shown. So once we do, we end up with this extra factor of 1/2. That came from this term. The first one was from what was in front of the integral to begin with. And maybe without showing all the details of that u substitution, we have successfully integrated 1/2 cosine of 2x to get 1/4 sine of 2x. I encourage the reader to carry out the details of the u substitution, maybe add that missing line that's in between these two steps to see what happens. But of course, that's Calc 1, so I'm not trying to focus on that too much. So in the end, we have 1/4 sine 2x plus 1/2 x plus c. And that's exactly our antiderivative of cosine squared of x. Now, the reader's encouraged to check this by taking the derivative and then using the half angle identity to get back to cosine squared of x. But that check is almost as difficult as performing the problem, so it's almost a little useless to do that. Down below, you do see the details that I was talking about for the half angle identity, so that's nice for reference. But you'll do that plenty of times this semester, or maybe you'll just remember the result highlighted down at the bottom as you go. So to recap this one, if we have all even powers of cosine and or sine, then we're going to need to use a half angle identity on one of those even powers of cosine or sine. And we can do this multiple times until we reduce it down to all integrands that are first powers of trig functions. So let's see what that might look like in a more advanced case. So here we have cosine to the 4th of x, and I'd like to integrate this, and we'll first start by doing the best we can with it. We say cosine to the 4th x is cosine squared of x, quantity squared. So we'll nest these. If it was cosine to the 6th x to begin with, we would have cosine squared x in parentheses and a power of 3 out here in the exponent, in the outer exponent right there. Okay, so luckily we only have n equals 4, so it's cosine squared x, quantity squared. Our first half angle identity lets us replace cosine squared x with this expression. And that quantity is squared, so we carry out the square of this, and we've got the trinomial that follows here, 1/4 cosine squared 2x all the way to plus 1/4. Remember that the middle term comes from outer times inner and inner times outer. And next we split this over sums. Since we're integrating over a sum, we'll have these 3 integrals. And notice the last 2, this one and this one, are easier to do, to calculate. Integral cosine 2x, we can look at our work previously to handle that. And then we look to the left and realize, well, we're not quite where we want to be. We still have a cosine squared to manage. So what we'll remember, though, is we've dealt with this before. We've integrated cosine squared of x. So why don't we piggyback this problem or this work on the work we've previously done? If we use a u substitution of u equals 2x right here, then we'll have cosine squared of u du ultimately, with some constants that'll turn up. And we'll be able to use our previous result here. Now we just have to manage the constants that might come out of this. So if u is equal to 2x, then du is 2 dx. So our substitution for dx is 1/2 du. So this dx will become 1/2 du. And we see that happening below. 1/2 du came from dx. And we have cosine squared of u, since u is 2x. So we just factor the 1/2 to the front of the integral. Again, using the linearity of the integral. Constants can be factored out of it. And then we recall that on the previous page, the integral of cosine squared of u is 1/4 sine of 2u plus 1/2 u. And of course, that's swapping out u for x from the previous problem, but it's just a variable, so it's easy to do. Now, in our case, we're going to have to come back into x from the u that we have here, but that'll happen momentarily. So the constants are being managed. Notice the other integrals were taken care of a while ago up above. These are just details that can be tracked down by the reader. It's good to rehearse this problem later after you've seen the video and check that you get the same answer. But these are Calc 1 integrals off to the right. And summing them all up after we take care of all the constants and adding up all of these three integrals with a plus c, the constant of integration at the end, we arrive at the following. So again, our work is nested on previous work. Each time we have a newer version of a problem or a more complicated version, we learn the next step. And in this case, the first thing that happened that we learned was to factor this in such a way that you have a sine squared or cosine squared within parentheses, and then the rest of the powers are taken care of by an external power of 2, 3, or whatever it is to make us whole on whatever this power was. Okay, the next step then is to use within the parentheses this half angle identity. Then you'll carry out whatever this power is, 2, 3, 4, whatever. You'll have to do that many binomial expansions. It could be a little bit messy, but you could use the binomial theorem to help with that. And then you proceed from there. And then you decompose what's left, or you use results from previously done integrals. There is a reduction formula also that can be derived. I think the textbook does it. It's encouraged that the student derives a reduction formula for these, or at least just keeps track of the one that's in the textbook. Okay, so in the next video, we'll look at integrating functions of the form secant to the n of x and tangent to the m of x, and that'll be part 2 of 2 in the video for 6.2a.